Hello guys, welcome back to another video on my channel. It's been quite a long time, but I'm back again. In the last video, we proved Lobachevsky's integral formula for an even periodic function. And as promised in this video, since the last one was a little proof-based and abstract for most viewers, I promised to do a few examples with this powerful tool in our arsenal. So let's get started. Let us recall the formula we had from before. It was integral 0 to infinity sine of x over x f of x such that f was even periodic. So that means f of pi minus x equals f of x equals f of pi plus x. And continuing this, you also get that f of x is equal to f of minus x. That's why I say even. That if f satisfies those conditions and we have an integrand like this, then that just evaluates to integral from 0 to pi over 2 f of x dx. Now, the first example is, let's say we have an integral I1, which is from 0 to infinity sine of x over x plus x cosine squared x dx. We can always factor out the x in the denominator to get integral 0 to infinity sine of x over x and the remaining function 1 over 1 plus cosine squared of x dx. And comparing this with the form that we have here, f of x becomes 1 over 1 plus cos squared x. So we can check that this function, and especially the cosine squared x, is even and pi periodic like that. If we didn't have a square, this would not hold true, because indeed we'd get a minus sign for pi minus x and pi plus x. So using Lobachevsky's integral formula, I1 just becomes integral 0 to pi over 2, 1 over 1 plus cosine squared x dx. This is quite a standard integral, and to evaluate this, we divide the numerator and denominator by cos squared x. So I get 1 over cos squared x, which is secant squared x, over, we have 1 over cos squared x, which is secant squared x, and cos squared x over cos squared x, which is the one here with the dx. Secant squared x can be written as 1 plus tan squared x, using the square relations between the trigonometric functions. So we get integral 0 to pi over 2 secant squared x over 2 plus tan squared x, because secant squared is 1 plus tan squared, and 1 plus 1 is 2. Dx, of course. Substitute u equals tan x, then du is secant squared x dx. So the entire numerator is just du, and the denominator is 2 plus u squared. The upper and lower bounds then just become 0 to pi, 0 to infinity, sorry. Because at pi over 2, tan pi over 2 is infinity. And then evaluating this, you can either do a trigonometric substitution if you don't remember the formulas, or if you remember the formulas, 1 over square root 2 inverse tangent of u over square root 2 from 0 to infinity. At infinity, we get pi over 2. At 0, we get 0. So just evaluate the value at pi over 2 for the arctan of infinity. So we get pi over 2 root pi. And that's it. We've solved this complicated looking problem by the use of our newest weapon, which is Lobachevsky's integral formula. Moving on, the second example is a little shorter. So I2 is integral 0 to infinity, absolute value of sine x over x dx. We can immediately see f of x is absolute value sine of x. And again, because of the absolute value, we have an even pi periodic function sine x. Because without the absolute value, sine is an odd function, even though it satisfies the pi minus x, pi plus x periodicity. So I2 by the Lobachevsky's integral formula is 0 to pi over 2, absolute value sine of x dx, which equals, now from 0 to pi over 2, sine of x is always positive. So we can just lose the absolute value. And we have integral sine of x dx, which is negative cosine of x from 0 to pi over 2. And that is simply 1. That's quite nice, actually. And then the final example is a little more involved, but it's quite beautiful. It will combine, of course, the main method along with a classic old method that we have been using on this channel. So I3 is integral 0 to pi infinity tan inverse of sine x over x dx. I3 of a, let's define a parameter, one parameter family. I3 of a is integral 0 to infinity tan inverse of a sine of x over x dx. So we've just introduced a parameter a here as opposed to what we had before. So how does this relate to the one we had before? Well, I3 is just I3 evaluated at a equals 1. Okay, fair enough. We're working with a more general situation. How can we use Lobachevsky? Well, multiply and divide by a sine. So we have integral 0 to infinity tan inverse a sine x over sine x times sine x over x dx. So we are indeed multiplying and dividing by its sine, because that sign wasn't there in the original expression. And then we indeed see that f of x, comparing to the standard Lobachevsky integral form, is inverse tangent of a sine x over sine x. You can check this is even pi periodic very simply, because there's a sign here and a sign in the denominator, and essentially an odd function divided by an odd function. The entire thing is even. So I3 of a is just integral 0 to pi over 2 from Lobachevsky's integral formula, tan inverse of a sine x over sine x dx. Now let's differentiate with respect to a, akin to the Feynman method. So that's why I said there's two methods here. We have a Lobachevsky simplification and a Feynman parameterization, and now differentiation. I3 prime of a is integral 0 to pi over 2, 1 over 1 plus a squared sine squared x dx. So now this is again like the first example that we did in this video. So just divide the numerator and denominator by cosine squared x. You get integral 0 to pi over 2 secant squared x over secant squared x from the 1 plus a squared sine squared x over cosine squared x is a tan squared x. So a squared tan squared x dx. Again, the same substitution, u equals tan x du is secant squared x dx. So we have, and this should have been I3 prime here actually. I3 prime of a is integral 0 to pi over 0 to infinity now because of the u substitution, du over 1 plus a squared plus 1, the whole thing times u squared. And now using the formula, 1 over square root a squared plus 1, tan inverse of u times square root a squared plus 1 from 0 to infinity. At 0 doesn't matter, tan inverse of 0 is 0. So at infinity we just get a pi over 2. We have pi over 2 square root 1 plus a squared, but that's just I prime, I3 prime of a. To get I3 of a, we have to see that I3 of a is just I3 of 0 plus integral 0 to a I3 prime of t dt from the fundamental theorem of calculus. I3 of 0 is indeed 0 because we have arctan of 0 So we just had to evaluate this integral of 0 to a, but we know what I prime is. It's pi over 2 square root 1 plus d squared dt, because the integration variable is d instead of a. That again has a standard nice form of pi over 2 sinh inverse of a. So I3, which is I3 evaluated at a equals 1, is just pi over 2 sinh inverse of 1. And that's it. We solved this problem. This problem actually looked really bad on the outset. You would wonder how to even proceed if this appeared on an integration B competition, for example, and you didn't have this nice Lobachevsky shortcut formula for you. I think there's a few brilliant steps in this example. First is to get Lobachevsky, we divide and multiply by the sine x. And once we do that, that's not enough. We actually treat it as its own problem and do a Feynman method with that one, introducing this parameter so that the sign vanishes when we take the derivative in the denominator. And then yeah, just everything else is standard integration stuff. So that's it for this video, guys. It was a short video. I probably wouldn't have made it, but I said it's been a long time and I might get busy in this period, so let me do something. Please like, share, and subscribe to my channel, recommend me to your friends, and just keep doing math. Peace out.